Alright, welcome to the Artificial Scientist. My name is Michael Bennett. I'm a PhD student at the Australian National University. This paper is concerned with the application of AGI to science, and among proposed means of verifying AGI, Goetzel's 2014 survey listed the Artificial Scientist test, which stipulates that an AGI will have been achieved when artificial intelligence independently produces research sufficient to win a Nobel Prize. While there's a wealth of research on AGI in general, what would be required to satisfy this test remains a little less clear. This paper attempts to clarify what exactly is necessary to create an artificial scientist, and how this fits within existing approaches to AGI. A scientist may be many things, but for our purposes a simple and unambiguous definition is best. The Royal Society's motto, Nullius in Verba, serves nicely, translated as take nobody's word for it, and emphasizes that a scientist establishes truth through experiment, not testimony. For this, our agent must possess certain qualities. This is not a list of every quality an artificial scientist ought to possess, but an attempt to identify what is necessary. First, we consider representation of hypotheses. We'll define a hypothesis as a statement which has a truth value and is falsifiable. A subset of such statements are readily testable, suitable subjects for scientific inquiry, and will not concern ourselves with the specific language used to represent a hypothesis beyond stating that an artificial scientist must possess some means of representing it. It will also need inductive inference. The Royal Society's motto, after all, is an explicit rejection of testimony as the basis of any claim. An artificial scientist must not rely on testimony. Without testimony, what is true must be inferred through observation, and so the ability to perform inductive inference seems necessary. It'll need deductive and abductive reasoning. Having inferred something of what is, the agent may transform this information without speculation through deductive reasoning, and then, from what is, our agent could abduct all that may be true, but uncertain. A testable hypothesis is one such thing, abducted from what is known. It seems necessary, then, for our agent to engage in deductive and abductive reasoning. It will also need causal reasoning and explainability. The purpose of an experiment, after all, is arguably to test a hypothesis, isolating cause and effect. And this is desired in order that humans may develop the technology to reproduce or prevent that effect at will. A provisionally accepted hypothesis explains phenomena. An explanation is only useful if it can be understood by its intended audience, and so a scientist must be able to communicate their hypotheses and results, and the significance of those results, in terms of what its audience values and understands. Mere interpretability is insufficient for more complex phenomena, as interpreting even simple symbolic models of well-understood subject matter requires a great deal of expertise. Pushing forward the boundaries of scientific achievement would produce models of such complexity as to be beyond the capabilities of human interpretation. So fluency in natural language seems desirable. It will also need to be able to evaluate hypotheses. A hypothesis must at least be falsifiable, and there is a cost to consider in the search for hypotheses. The question is which hypotheses ought to be abducted. Hume's guillotine tells us you cannot derive an ought from an is, and so we must give our agent an ought by which to judge hypotheses. If one is to choose between several hypotheses, then the truth of any one of which would serve to explain some observed phenomena, then it seems reasonable to assert that one should start by testing the most plausible, the most likely to be true. As for experimental design, evaluation, and planning, to test a hypothesis, one should design an experiment that isolates and tests a hypothesized cause and effect, so ideally controlling for other variables, and each experiment costs resources, and information gain should be evaluated in terms of expected benefit across all hypotheses versus these costs. So, an agent must identify what novel information would confirm or disprove the adducted hypotheses of the greatest expected utility. It must design experiments that will convey said novel information and compare and plan experiments based on the opportunity cost. And finally, to perform an experiment, an agent must possess a means of interacting with the environment. The process of experimentation could be perceived as an active cognition, which posits cognition arises from the interaction of an organism with its environment. This assumes cognition is embodied, embedded, to function within the confines of a specific environment, enacted through what an organism does, and finally, extending into the environment to store and retrieve information. All of this seems obviously necessary to conduct experiments in the environment. We're not offering an unqualified endorsement of embodied cognition. After all, it's arguable that even a laptop has a body. However, experimentation has certain physical requirements, and if one is able to perform targeted interventions that attain specific novel information and isolate causal relations, the process of learning may proceed much faster than if one is forced to wait around for novel information to be observed. Next, we'll examine 3 relevant approaches to AGI and how they stack up against these criteria. To standardize the terms with which we compare these approaches, we employ a model of an arbitrary task and treat the application of intelligence as prediction, and so define each of these approaches as trying to predict the appropriate response given a situation. For the sake of brevity, these can be read using their common language definitions. First up is what we'll call a logicist approach. We'll use this as a catch-all for approaches that employ symbolic knowledge representation and inductive logic programming for learning. A finite set of symbols are used to describe a discrete environment, states, actions, and so forth. Symbols may be joined by logical connectives to specify statements that have a truth value within any given state. Degrees of belief in the truth of a statement, probabilities may be assigned to statements where the environment is stochastic or partially observable, and statements may also be employed as constraints to define what behavior is permitted. An agent may infer such constraints from examples through what is called inductive logic programming. As with Goetzel's symbolic category, a logicist approach typically subscribes to the physical symbol system hypothesis, meaning an abstract symbols it employs are assumed to be grounded in hardware. But how this is achieved is left to implementation. We go a step further and say that the logicist approach is perhaps better characterized as employing a constant and unchanging vocabulary of symbols, some of which are in some manner specified by a human, though their exact definitions may be learned. Such an agent typically learns rules that determine whether a chosen response is correct in a situation, and from which a response may then be derived for a given new situation, allowing the agent to generalize. This is as opposed to directly modeling responses as a function of situations. Next up, we have emergentist approaches, which do exactly that, model responses as a function of situations. They take as their premise that complex behavior and what we call abstract symbol systems may emerge through sub-symbolic processes. This process is called symbol emergence and typically uses approaches such as latent Dirichlet allocation to cluster multimodal sensory-motor stimuli into perceptual or sensory-motor symbols with fluid definitions akin to natural language. For example, researchers created an agent capable of associating the sound of a word cup with the image and other characteristics of a cup as experienced by the agent. But success in constructing more complex symbols, such as opera or belief, remains elusive. Finally, we have a universalist approach. In the context of an arbitrary task, an agent must map situations to responses, and such an agent could be conceived of as a program. A universalist approach assumes quite reasonably that for each environment or task, there exists at least one program that always chooses the best possible responses, maximizing reward. And so there must exist a program that maximizes reward across all environments or tasks. To define this program, Hutter employed a formalization of Occam's razor, named Solomonov's universal prior, which assigns a weight to every program which reconstructs what the agent has experienced of the environment thus far. The same model could be expressed by programs of varying length, and so each program is evaluated by its Kolmogorov complexity, the smallest self-extracting archive in a specific language. This agent, named AGI, performs such that there is no other agent which outperforms it in one environment that can also equal its performance in all others. In other words, AGI may be outperformed in a specific environment by a more specialized agent employing a strong inductive bias that prevents it from performing as well across other environments. This approach is distinct in that it begins with a guarantee of optimal performance in terms of an arbitrary reward criterion. The downside Solomonoff induction is incomputable. So, are any of these three approaches alone sufficient? If we look at the universalist, by choosing the smallest self-extracting archive as its model of the world, AGI is in effect choosing from amongst possible hypotheses the most plausible. Certainly AGI is capable of inference, and by extracting predictions from its highly compressed representation of the environment, it seems reasonable to assume there must be something analogous to induction and deduction taking place. And finally, by taking the most compressed representation, it's certainly identifying the most plausible hypothesis according to Occam's razor, and is likely to isolate causal relations. But on the downside, AGI, even if it could be approximated well enough, behaviors such as explainability must all somehow be specified by the reward function, and creating a function that guarantees such complex behavior may not be any more achievable than AGI in general. Next up, we have the emergentist approach. In the 4 category, the utility, or at least popularity, of emergentist approaches such as deep learning and in narrow industrial applications is fairly indisputable. Models such as GPT-3 demonstrate that even complex writing tasks are not beyond the reach of existing technology, and while such models do tend to be difficult to interpret, if they can be made to infer ambiguous rules underlying natural language, then perhaps they can eventually be made explainable to a layman. Certainly an emergentist method is easily implemented in a physical robot because there's no abstraction required, and if a human language is in all its inconsistency to be acquired by an AI, then an emergentist method seems a promising approach. But against this, an agent that only mimics plausible explanations is of no more practical use as a scientist than an agent that gives no explanation at all. We can only trust explanations as far as we can interpret and verify them. For example, the aforementioned GPT-3 seemed to acquire basic arithmetic, but as soon as it was presented with less common sums and equations, it started giving responses that were clearly wrong. It appeared to mimic arithmetic whilst having failed to grasp its underlying rules. This may also be why many popular emergentist methods require so much data to learn in comparison to existing logistic or universalist methods. An agent that only mimics must learn all correct responses by rote, while an agent that understands what determines correctness of all responses will be equipped to identify the correct one in any situation. Finally, logicist approaches. In the 4 side of things, a hypothesis represented as a statement within a predefined symbol system is interpretable, although it must be fairly simple. And though SAT is NP-hard, a suite of existing solvers allows one to search the space of possible hypotheses in a lot of problems fairly efficiently and with guarantees of optimality. Constraints are easily specified in comparison to other methods, allowing one to tailor agent behavior to better suit specific tasks as such as experimental design and planning, meaning we could tailor the agent more easily. Finally, not only is this technology to deduct, abduct, and infer with symbolic representations mature, but causal relations and their computation are, also coming along in this area and remain easily verifiable after the fact because you have this clear representation of the information. But against this, abstract symbols must somehow connect to low-level sensory-motor stimuli, must be grounded. Even if this is somehow solved separately and tacked on to the end of a logicist approach, any fixed set of symbols may be far from suitable to express explanations for which we require an artificial scientist. Even if this was solved, such explanations are unlikely to be understood by even the most qualified humans. It's not tailoring what it says to what its audience understands or wants. What is less obvious about cognition is why symbols are formed as they are and which abstractions are best for a given task. An emergent symbol system may be part of the solution to a task, expressing specifically those things of relevance in solving it. And finally, the simple act of representing a hypothesis symbolically does not mean that it's the most accurate hypothesis explaining the data, and something akin to the formalization of Occam's razor employed by universalist methods remains necessary. unifying perspective. So, none of the aforementioned appears sufficient in isolation, at least in the near term, for the purpose of constructing an artificial scientist. However, they all address various characteristics we deemed necessary. A universalist approach reveals what hypotheses are most plausible. A logicist approach facilitates interpretable representation of hypotheses, reasoning, and the ability to tailor behavior to our needs with ease. And an emergentist approach facilitates enactivism and the possibility of an emergent symbol system which is, fluid and comparable to natural language. The two complementary bodies of research might provide a foundation for future work along these lines, combining these approaches. The formalization of an arbitrary task and its solutions, named the Solutions 20 task, and a formalization inspired by the work of Kant, named Kant's cognitive architecture. These approaches are similar but based on different premises, providing different insights. Both attempt to infer a hypothesis which explains the observed data, from which correct responses to every situation might be abducted, and combined with a solver to abduct responses, such hypothesis qualifies as sort of lossless compression. Finally, neither approach relies upon abstract symbols. Learning from sequences of sensory data in the case of Kant's cognitive architecture, which has been implemented in the form of the apperception engine, and a set of sensory motor states in the case of the Solutions 20 task. To go into a little more detail on Kant's cognitive architecture, taking Kant's critique of pure reason as its inspiration, this asserts that there is no such thing as a specific judgment. Subsequently, every rule is universally quantified, or doomed to generalize, as the authors put it. Evans, the author, introduced the notions of unity, a form of inductive bias that specifies which constraints are acceptable in terms of spatial, temporal, and causal relations, along with object permanence, which he calls static unity. The solution is then made more general by choosing weak constraints. Such notions are well suited to explain all sensory data in general terms, and their implementation in the form of the apperception engine performs as one would expect, pretty damn well. The resulting hypotheses are maybe not the most general, but enough so that we can say that it accounts for something of the universalist's notion of plausibility, like Kolmogorov complexity. It's arguably embodied to some extent because it's concerned with sensory data, but it doesn't account for the motor part of the sensory-motor equation, as is reflected by the specific choice of inductive bias. It's concerned with predicting sensory data, and the rules that he's enforced reinforce that. As for the other approach, the Solutions 20 task, this is a bit more general, raises the notion of an arbitrary task, which it attempts to formalize, and its solutions. The assumption being that it must be possible to succeed or fail at a task to some degree. The domain of possible solutions to a given task contains two sort of extremes. One is the intentional solution, which is sort of the most general. More like instead of framing Occam's razor in terms of formalizing it in terms of the length of a program, it does it in terms of the weakness of a statement. So the intentional solution is made up of the sort of weakest component parts, and the extensional solution, which is made up of the strongest component parts. So this would be like comparing the rules of chess, from which every legitimate game could be abducted, to the simple enumeration of every legitimate game of chess. They're necessary and sufficient to imply each other, but one of them is a set of generally applicable rules. Because the task is defined in terms of sensory motor states rather than sequences of sensory data, the solution is more general than this, pertaining to interactive sensory motor control and intervention rather than just the prediction of sensory input. Finally, it attempts to solve the symbol emergence problem directly by arguing that the most general statement represents the intent of a task, and then goes on to explain both symbol emergence and the modeling of intent in other agents. this is computable if given if restricted to a specific hardware, limited expressive language, as yet there's no working implementation released. So to compare these two a little bit, they're not mutually exclusive but complementary. One of these sort of frameworks gives a slightly more general take on tasks, including the motor aspect of things. Given a subset of possible tasks pertaining to specific types of sensory input, the inductive bias implemented in the apperception engine of Kant's cognitive architecture would result in what the solution to any task would call an intentional solution. And for some other tasks, the apperception engine might spit out something a little closer to intentional than extensional. But for some kinds of tasks, particularly those, the strong inductive bias given is heavily biased towards sensory data. So it's just going to come up to the right answer for that style of prediction task. Ultimately, our artificial scientists should prefer a more general approach in which hypotheses are the most plausible, regardless of the task, within reason. Meaning that being based on Occam's razor might be a bit of a better approach, even if it's difficult to implement. However, that said, a working implementation of the apperception engine is publicly available right now. It's not an abstract promise of future capability. As to comparison with respect to experimentation, the specifics of experimental design are not addressed in either case. So regardless of inductive bias, experiment does remain necessary to guarantee, the sort of most efficient learning, and to find the most correct hypothesis to get towards causal relations as quickly as possible. And finally, with respect to symbol emergence, Kant's cognitive architecture does not really even attempt to address this. Evans has proposed the integration with subsymbolic methods such as neural networks to ground these abstract symbols and written a paper on that. These could then be composed into the concepts they talk about in the apperception engine, albeit still limited by that inductive bias towards sensory input. This all seems to imply a sort of constant and unchanging sort of language of abstract symbols, but it's certainly a step in the direction of an emergent symbol system. It at least integrates some of it. However, the solutions to any task posits that not all symbol systems are equal, and some may be better suited to describe what is relevant in a particular task than others. Such a symbol system is implicit in the solution to a task, clustering sensory motor states in terms of what is relevant to success in a given task. This attempts to address not only symbol emergence, but the modeling of intent in other agents to try and understand what an agent one is communicating with desires, what their sub-goals are. And so you could tailor an explanation to what your audience understands and considers important. Of course, this is a lofty, far-off goal. Such a symbol system means, however, that symbols are not learned separately from one's model of the world, which is a different approach to simply tacking an emergentist method onto the front of a sort of more logicist method. All right. Well, thank you very much for listening.